Start again. Thank you all for coming to Origins today. It is my pleasure to introduce Theo Richardson. Theo was an undergraduate at Cornell working on millimeter and submillimeter instrumentation with a person whose name I forget. I'm so sorry.
Gordon Stacy.
Gordon Stacy. Theo is now a sixth-year graduate student at the University of Florida, working with Adam Ginsberg on star formation and particularly SED modeling of star formation, which is what we are going to hear about today, a theory agnostic framework for SED modeling, which, having done this work, I can tell you is deeply exciting to the star formation community. So go ahead and take it away, Theo.
All right. Well, thank you, everybody, for coming out to listen today. And for our online folks, thank you very much for tuning in. I'm excited to be here.
Do you mind turn on your video so that people only consider?
I would love to, but my camera doesn't work. So if you want to see me, here I am. Hello, this is what I look like. Sorry, I'm going to be facing this way for the majority of the talk, but if you've got questions, I'll do my best to actually try and show my face for that.
I did tell him he could sit there, so.
I'd be being a bit more mobile if things were technically working out. Boy, it's just been a banner week for everybody, hasn't it? We had a hurricane out our way. I don't know if you heard about it, but it got us pretty good over in Gainesville. So I have been dealing with a lot this week, which is why it's great to be here telling you about a framework for modeling the evolution of young stellar objects. This is work that comprises the majority of what I've been doing as a graduate student at the University of Florida. So it is deeply exciting to take it on the road and shop it around. And without further ado, let's start at the end, shall we? This is the IMF. It is something that you've probably seen before, but as a general introduction, it is the mass distribution of newly born stars, or put another way, for some cloud of gas and dust that is going to collapse and form stars. This expresses how many stars of a particular mass you should expect to form from that cloud. Where we've gone out and measured it, it looks generally like this, where there's more low mass stars than there are high mass ones. But more on the measurements in a second. Now, the thing about this is that if we were able to actually look at the masses of individually resolved stars all over the place, the IMF maybe wouldn't be much more than a curiosity. I mean, it might still be important, but the thing that we really want to know about a star is its mass. It determines how it lives, how it dies, and how it influences the environment around it. But here's the problem with that. Once you get far enough away, this nice individually resolved population of stars starts looking a lot more like this. Where now you need to go from the combined light of an entire stellar population to back out the individual constituents if you want access to that same level of information about the actual region itself, which means that you need an IMF in order to get that information. So I say you probably heard of it before because it turns up all over the place. This is an incomplete list of quantities that are very important in galactic and extragalactic scales that rely on an IMF often in order to even begin to measure, because it plays a part in setting expectations for what we should be seeing if a given thing is true. There is a given stellar population that goes on to make up an unresolved amount of light that we're seeing. As an example of the power of the IMF or how it influences measurements that you make, this plot from Kapil et al. 2013 shows mass to light ratios of galaxies that are both inferred through dynamical measurements of the stars in the galaxy and also through the use of a salpeter IMF, which is one of the commonly used functional forms that gets bandied about. There are a few, some of which you've already seen, but if you change which of those functional forms that you use, well, that changes where on this plot you expect the galaxies to appear, meaning that fundamental properties of these galaxies that you would expect you'd want to know depend on this background concept that goes into setting expectations. And in addition to the long list of features, the IMF is also a window into the theory of star formation, which is currently, as it stands, a subject of ongoing debate as to the precise mechanics of how you get from a cloud of gas and dust to a star. There's lots of theories that have been proposed, but if a theory can reproduce a mass distribution of born stars that looks kind of like the IMF, that's usually held up as evidence that it's motivated, that it's reasonable, right? So it is a very important quantity to know for a lot of different reasons, which is why I'm very sorry to tell you that it's not super well constrained, because it is a difficult thing to get at directly, right? The purest expression of an IMF that you would want in order to measure is to go out and look at stars and count them, right? But here's the problem with that. If you go out and look at formed stars, you will not get a complete population. Low and high mass stars live and die on completely different timescales. So what you're actually measuring is the present day mass function after the high mass stars are dead, which means that you have to go from what you actually see and infer what the IMF actually was, or what the IMF is at the base of it. And that is subject to inference and uncertainties that can emerge from that. As well, there are observational effects that can confound your ability to measure the present day mass function, binaries, mass segregation, extinction, all that sort of thing. So direct measurements are not as direct as we might otherwise like. And while a number of other methods have been developed to get at this quantity, they are all even less direct than that. And they require a lot more inference in order to get to what we actually want. Again, referring to this plot, this is mass to light ratios of galaxies, which, I mean, there's two different ways of doing this on this plot alone, right? So I think it's reasonable to expect different people to have different opinions on how to actually get to the IMF from this, right? That's not great for us because, again, it's a very important quantity that would be very nice to have a constraint on. And at this point, I'm going to introduce a sister concept, the core mass function. Like the IMF, this is a mass distribution, but instead of the mass distribution of newly formed stars, it is the mass distribution of pre- or protostellar cores, stellar precursors that'll go on to collapse to form stars in the picture of star formation that we built up. Where this has been measured, as an example, in the Pipe Nebula in August of 2007, the shape is evocative of the common shape that we assume for the IMF, or that we've measured so far. And that is potentially a great thing, because it's intuitive to look at this and think that there is a connection between these two concepts. And that connection could be very helpful in actually getting to measurements of the IMF, because unlike the IMF, the core mass function, I think, is more reasonable to expect higher completeness if you're able to get to the actual constituent cores that are forming in a region, right? A region, if it cools down enough to form stars, you can expect it to generally happen on the same timescale across the mass spectrum, unlike the lifetimes of high or low mass stars. So in the picture where a core goes on to form a star, the core mass function is a direct conduit to the IMF that deals with a lot of issues that other measurements have. However, you have to actually form stars to get from point A to point B here. And as I've already said, that is a subject of debate. This is an inexhaustive list of open questions in star formation. I won't read them all out for you, but I will point to the schematics on this plot from the Offner et al. PP6 review, which sort of detail ways in which, starting from the same core mass function, if you change your answer to questions like these, a different IMF will result from even the same starting population. So, if things fragment differently than you expect, or if the efficiency of mass accretion is not similar across the entire mass spectrum, or if not all cores are pre-stellar, you get something very different out from what you expect just by looking at the core mass function. So it would be great if we could, I don't know, produce a modeling tool that was capable of accommodating all of these different scenarios, right? Because that would allow us to actually go out and determine which of these scenarios are consistent with what we actually observe. And if that's what you're thinking right now, well, that's crazy, because that's exactly the kind of thing that I'm trying to do. So the objective of my work to date has been building the infrastructure to answer the question of how these two concepts are linked, if they are linked at all. And assuming that I am able to establish a good answer to this first question, that'll enable me to go after the big game, what the IMF is to begin with. So these are the stakes. Now let's talk about what I've actually been doing. To model the connection between the CMF and the IMF, what I've been doing is essentially breaking the CMF down into its component parts, individual young stellar objects, or YSOs, and chasing good models of those. Now, YSO is a term that I'm going to define here for the purposes of this talk. It is a catch-all for the combined system of a source of luminosity that is going to go on to become a star and surrounding gas and dust. That's broad enough, I think, to generally capture what most people mean when they say that, and also to capture the scope of things that a YSO can be in theory, as you'll see in a moment. So with that definition, these are crucial things to be able to understand if we want to know how stars form, because they are forming stars, right? So there's already been a lot of work dedicated to modeling these. I want to focus on a particular attempt at doing that, starting with the set of YSO models published in 2017 by Tom Robitaille. This is a very large set, and it is broken down into subsets based on the presence or absence of particular dust density structures. You might be familiar with this, but again, as a general overview, these cartoons give you a sense of the ways the subsets, which I'm going to term model geometries or geometries going forward. Some geometries have just a bare star, some geometries have disks, some geometries have envelopes, sometimes those envelopes have cavities, but regardless of the structures that are present, each model has associated shape parameters which determine how these things are shaped. So that's things like disk scale height, envelope density scale, cavity opening angle, source radius, that sort of thing, and an associated SED calculated with the radiative transfer code Hyperion. And another important thing to note about this set of models here is that all of those parameters that I just talked about are randomly sampled. Every model is just randomly sampled, and that's run through radiative transfer, which is qualitatively different from how a lot of other attempts at making things like these handle it, which I'll come back to, but it's very important for our purposes. But this actually isn't the set of models that I want to talk about. The one I want to talk about is mine. Earlier this year, I published a major update to this Robitaille set of models that now includes a lot of additional information that wasn't present in the original release. For example, not all of the models that were intended to be part of the Robitaille set actually came out in 2017 because the computational cost was too high. There just wasn't enough access to resources. I have access to more resources than that, so I have been plugging away at getting models that weren't released originally into the set. In addition, I've also added a lot of other information that one might want to know about these models. See, it was mostly limited to shape parameters, right, which are great as far as the shape of the YSO, but they don't tell you things like how much mass is contained in it, how hot the dust is, how stable the disk is, or how much sightline extinction there is from certain stellar material, all sorts of things like that. I've also added a lot of convolutions for new instruments, including JWST, which you might have heard of, and used the information that I've added to go through a lot of second order properties about the models that also help in interpreting its general physical state. Now, this is going to help us build our framework for modeling the evolution of young stellar objects, which is where I'm going. But there's a lot that you can get with just this alone. So with your indulgence, I'd like to talk about a few of those now. Starting with testing some assumptions about how we measure properties of YSOs. A thing that you generally want to know about a YSO is, again, how much mass is contained with it, especially if you're trying to measure something like, I don't know, the core mass function, right? That's what that is, the core mass. So a common technique for doing these mass measurements is to A, assume that the dust is optically thin enough at long wavelengths to use, B, this equation to infer the mass of the core from the observed flux. However, there is a second assumption that is being made here that is necessary to actually get to a mass, and it's this guy, the dust temperature. This is a thing that's hard to know about a YSO just from looking at it without bringing in some outside information. And so oftentimes, you have to just assume a single value and hope that it works. And oftentimes, that single value that you assume is 20 Kelvin or thereabouts. Here's the thing, though. With this set of models, I've got a very, very large base of examples of this to draw from where I know literally everything in this equation, right? I've got all of these. There's no unknowns here. So it's a prime opportunity to put this assumption to the test in my set. So that's what I'm going to talk about. What you're looking at here is basically testing that assumption. Oh man, the shaded regions on projectors have not been my friends recently. I'll highlight it with the mouse when we get to talking about that. But first, let's start with the left plot. So this is comparing the mass that you infer for a set of models that has been specifically constructed to be optically thin and exhibit a 10 millijansky flux, roughly, give or take, within an aperture of 1000 AU radius at 1 millimeter. So these are models that all generally look the same. And this is comparing the mass that you infer through use of the optically thin dust equation and the actual mass that's contained in the models. And you can see that if we assume that dust temperature to be the weighted average dust temperature within each of these models, which I've calculated, the agreement is very, very good, right? There is a very strong correlation here between the mass that you infer and the mass that's actually present in this sample that's all optically thin models. So that means that this assumption is a good one if you're able to pick a representative dust temperature. Great. However, this is not what people usually do because the mass weighted average dust temperature is you don't really know that just by looking at it. So let's test 20 Kelvin instead, shall we? And that's the plot on the right here. So this black line is essentially corresponding to an assumption of 20 Kelvin dust. And these shaded regions that I've plotted here are corresponding to a 50% interval within the true value. And you can see that most models, looking at this gray shaded region here, do not occur in it. They mostly are very, very overestimated by inference of mass using 20 Kelvin dust. So it's not representative of this sample in the slightest. However, they seem to be bunching up a lot here around this other line. So if we assumed this dust temperature instead, which is 40 Kelvin, the median temperature of models in this sample, does that work better? Well, let's take an alternate view of this plot. So this histogram is showing this sample from an alternate angle. And the filled region here is essentially all of the models that you were just looking at, but plotted by the ratio of the inferred mass to the true mass, all where the inferred mass is all with 40 Kelvin dust. And looking at that histogram, it looks pretty good. And generally speaking, you are able to get within about 50% of the true mass of all of these models most of the time, or at least the 1 sigma region of this Gaussian that I fit to it is about 50% of the true value spread. So that tells us that this assumption is good and does get us representative masses if we are able to use a dust temperature that's actually representative of what we are looking at. Again, assuming that it's optically thin. If it's not optically thin, you get this unfilled histogram in the back where you way underestimate the amount of mass that's actually present because, well, it's hidden. But that raises the question, how do we actually get that dust temperature? Well, I've repeated this analysis for a lot of different sets of models constructed that exhibit particular fluxes within particular apertures. And this is what I found. So these are the median dust temperatures with some error bars that get you an inferred mass that is, generally speaking, within 50% of the true mass most of the time for different combinations of aperture size and 1 millimeter flux. And this represents, I think, a pretty big leap forward in our ability to get good measurements of the masses of cores, because this gives you a basis for what you should expect if you see something that looks like one of these cases. So this gives you a roadmap for, if you use my set of models to sort of repeat this analysis, what dust temperature is representative for your case, or if your case is already represented on here, what dust temperature you should use when you're going out to try and infer the masses of cores. And that's great. It's a result that was not possible with the previous version of these models, or a lot of models actually for that matter, that has pretty big ramifications for a basic assumption underpinning a lot of current observations of forming stars. And that's not even all, because now I'd like to talk about the concept of classes and stages. So there's a lot of disagreement on the precise path that a YSO takes to become a star, but we've built up a general picture that is qualitatively in agreement, where a YSO goes through several distinct phases that describe particular evolutionary stages in its life. These are theoretical concepts that describe what is physically happening to a YSO as it evolves to a star. So there is a phase, there's a stage where most of the mass of a YSO is concentrated in its envelope. There is a stage where most of the mass of a YSO is concentrated in its star and disk, so on and so forth. But here's the thing, again, you can't directly observe this. This is the thing that you actually want to know, but you can't see it. What you can see instead is its class. And classes of YSOs are based on commonly the infrared spectral index of a YSO. There's several empirically determined categories that a YSO can fall into that are commonly thought to correspond with the evolutionary stages, and in fact, often used interchangeably in the literature, those two terms. Here's a little more detail on the definitions of class and stage that I am going to adopt going forward. I'll spare you reading them at you, but I'll say generally that successive stages mean that more mass is transferred to the star, and successive classes see the spectral index getting more and more negative and closer to a pure stellar SED. And the story for how these two things are related goes a little something like this. So as a YSO starts evolving, most of the mass in the system is concentrated in the envelope, or at least not in the central source. And so most of the radiation that's coming from this central source will be reprocessed by the surrounding envelope, meaning that the SED that you see out here should be mostly dust dominated, i.e. it should have a positive spectral index. So this is a class 1 SED that is thought to correspond to a stage 1 YSO. As the YSO continues to transfer its mass onto the central source, the envelope is mostly dissipated, and you get to stage 2, which is where the YSO is mostly a star and a disk. And at this point, while there's still dust content in this YSO in the disk, there are also plenty of ways in which you can see now the stellar SED at the center, meaning that the spectral index should be more negative. You should get a class 2 SED. And as more mass is transferred to the YSO, it mostly clears its surroundings of any dust content that isn't just medium, and becomes stage 3, where it's just a bare star. And at this point, the SED should be mostly, if not entirely, stellar, meaning it should have a very negative spectral index. This is the story. However, I'd like you all to embark on a little bit of a thought experiment with me, if you will. This is a stage 2 YSO. We're all in agreement, right, that this is stage 2, like I just laid out. But I'd like you to consider, A, does this stage 2 YSO look the same along both of these sight lines, face on and edge on? And B, do you think you'd be accurately able to determine that this YSO was stage 2 in both of these cases? I'll give you a second to think about it. But if you ask me, I'm not sure, right? I think there's a case to be made here that if you look at this YSO, which is stage 2, this way, you're looking through a bunch of dust, meaning that most of the radiation that you should see has been reprocessed through the disk here, meaning that it could very likely does look like a class 1, which would mean that if you used class and stage to mean the same thing, you would be wrong about what this YSO looks like if you look at it this way. And I think this points at the potential for confusion between the class and stage of YSOs. And again, I have a whole set of models where I know all of this information, right? So let's take a look at what this class stage confusion can look like within the context of my models. And it looks like this. This is a confusion matrix detailing the classes and stages of every model SED within my set. The numbers are formatted as percentages of the total number of SEDs. So right away, you should be able to see that class 1 stage 1 and class 2 stage 2 are the most populated cells, right? And in general, there is a correlation from top left to bottom right, which is what we would expect if our picture of star formation is mostly representative of reality, right? Class 1 stage classes and stages appear to be related in the way that we think they are. But you should also see that there are many ways in which that agreement is violated due to observational effects, right? You can have extinction that makes your stage 2s look like class 1s. You can look along a YSO that is stage 1 or stage 0, but through a cavity, so that you're seeing more contribution from the stellar SED, making it look like a later class than it actually should be, if we're assuming the formalism to be correct. And in general, I think this gestures at ways in which the agreement between class and stage can be violated in theory. But I also wouldn't take these numbers too literally. This is just one model gets one contribution to this matrix. And as I've already said, a lot of the models in here, or all of the models in here, have randomly sampled parameters, meaning that there are probably a number of ones being included in this case that do not make sense from a physical perspective, or do not gel with an accepted physical model for how a star should evolve. Let's put a pin in that idea for now, but this generally shows how classes and stages might be confused observationally, which is, again, a good thing to be able to characterize because it underpins a lot of what we know about star formation at present. All right, so now that we've talked about the set of models and what you can do with just that, let's talk about actually modeling the evolution of YSOs using this set of models. And here I'm going to introduce another definition for protostar, which, if a YSO is the combined system of a luminosity source and surrounding material, I'm going to define the protostar as just the source. So just the thing that's actually going to go on to become a star, where the mass from the YSO is accreted onto. If you have a problem with that, that's just what it's going to be for the for our purposes here. But you're free to take it up with me later if you'd like. So this is another thing where there's been a lot of work devoted to making models of evolving YSOs to try and understand how they change with time. But most of those attempts follow a very similar playbook. To start, you would begin by assuming that YSOs evolve according to a particular theory of star formation, of which, again, many have been proposed. You pick one, you use that theory to generate a set of protostellar evolutionary tracks that tell you what a protostar should look like as a function of time, its radius, its mass, its accretion rate, and you would sample parameters along those evolutionary tracks to use those as input to radiative transfer models of YSOs, which would get you a set of models based on a particular theory that would tell you what a YSO following that theory should look like over the wavelength range of your SEDs as a function of time. You can see that happening here. This is a portion of a plot from Zhang and Tan 2018, which is a grid of models based on the turbulent core theory of mass accretion. And these lines are their evolutionary tracks, and these black points are where they've picked to sample parameters. So this is all well and good, and it gets you something that you can use to go out and start trying to constrain properties of YSOs and say something about where they are in their life cycle. But I do want to ask a question about those results, which is, how do you know that they're true? Because, I mean, what you're looking at, or what you're deriving is what the theory says a YSO that looks like that should be, right? That's what you're actually measuring. But those theories, well, for one, there's a bunch of them, and they're all simplified versions of the complex process that is star formation, right? There's a lot of variables that can affect things. Most theories pick a few things to focus on: turbulence, Bondi-Hoyle accretion, and really go all in on those. And model grids that are based on these theories are typically confined to pretty narrow slices of parameter space, of the full parameter space accessible by these models, right? Because you want to get a few physically sensible scenarios that jive with your theory, but oftentimes the parameters that are associated with these theories don't show up in other theories, and even where they do, they're in a pretty narrow window of acceptable theory space. So there is a question of what you can actually say about a YSO in a case where something doesn't fit, or more broadly, what you can say about the ground truth of the measured properties that you back out by SED fitting within the context of a single grid of models. As an example, these two plots that I put up are portions of a plot from one of Allison's papers, which goes over a set or a sample of extended green objects. And there is a section that fits the SEDs of those extended green objects with multiple sets of YSO SED models that have been generated according to different theories, or one of which is the Robitaille 2017 grid, which doesn't assume a theory. And the results are systematically different, right? If you go in with one of these grids, you're going to get out a very different picture of what is actually going on with those YSOs. The radii and luminosities are pretty different, and you draw very different conclusions about the actual physical state of the YSO this way, through the lens of a single theory. Let's dive in a little bit more into how that's possible. These are accretion rates that are predicted for a 1 solar mass protostar following 3 different accretion histories, models of how a protostar should gain mass with time. Isothermal sphere accretion, turbulent core accretion, on which Zhang and Tan 2018 is based, and competitive accretion. And a thing that is immediately obvious is that generically, these 3 do not agree with each other. So a protostar that is following any one of these accretion histories is going to look very different from the other 2, particularly in this case here, right? Isothermal sphere accretion, as parameterized here, is a constant rate with time, and that rate differs a lot early on and at late times. There's only a little bit of agreement between these scenarios. So you can imagine that if you base a model grid on any one of these theories, you're really missing out on checking what the other 2 look like, and whether or not any one of those is actually closest to what's happening physically for real. So it would be nice if you were able to, I don't know, do all of that modeling for within one infrastructure. And if that's what you're thinking, then once again, oh my gosh, that's a great thought. So this is where I'd like to outline my own framework for modeling the evolution of YSOs. Instead of starting from a theory and building a set of models on top of that, I start from a set of models that does not assume a theory and is very well sampled, and then impose multiple theories on top of that set. That process is happening here. So these black dots here are models from one of the geometries in my set. And this red curve here is an evolutionary track for an isothermal sphere accretion history for a 1 solar mass star. And these little colored dots here are models that are close to this evolutionary track within this parameter space. Now, this is a bit of a simplified version of what I am actually doing. This is one nearest neighbor model to this track from one geometry. In actuality, I pick from a set that includes multiple geometries that all have envelopes, and pick 10 nearest neighbors, and then average over the SEDs of those nearest neighbors to produce a prediction for what the SED of a YSO that is following a particular accretion history should look like as a function of time. So this represents, I think, a pretty notable difference from how it's traditionally done. And as an illustration of how, I give you this. So on this slide are evolutionary predictions for the 100 micron and 3 millimeter flux of a set of YSOs that I have generated that span final stellar masses from 1/5 of a solar mass to 50 solar masses as a function of time for 2 different accretion histories, isothermal sphere on the left, turbulent core on the right. And not only are we able to do this this way, which you couldn't do with any other set of YSO models that would be based on just one of these, but you can draw a pretty easy distinction between these 2 scenarios, right? I plotted some isochrones over these evolutionary tracks, and they do not occupy the same parts of flux space at even close to the same times, right? There is an obvious difference between turbulent core, which gets here much earlier, than isothermal sphere, which gets here much later. And this goes out to like 30 mega years in the parameterization that I am using here for the most massive YSOs in this set. So yeah, if you look at a population of YSOs that has a reasonably well-constrained age and you put them on this plot, you should be able to tell pretty easily which one of these 2 scenarios is closer to the ground truth, which in turn tells you more about what the YSOs that are, making up that population actually look like, right? This represents a way to constrain the properties of YSOs on an axis that has previously been pretty hard to access or requires pulling in multiple sets of YSOs.
It was a fun 2 years.
Which takes 2 years. This takes you seconds, it's great. So I'm very excited about the prospects of these, but perhaps it's wise to pump the brakes a little and ask, does this approach actually yield good performance, right? If we predict something, does it represent, something that we expect to see for a particular part of the parameter space that we use? We select on a 3D parameter space that includes the temperature, luminosity, and core mass of a YSO. So does that actually, work? Well, let's talk about that a little. So on this slide are some attempts at cross-validating our approach on existing SEDs within our set of models. So this is 2 SEDs from one model in our set, both face-on and edge-on, left and right respectively. And in blue and in gray are our reproduced SEDs from averaging their 10 nearest neighbors in our parameter space. And in the wavelength regime that we were just talking about, which is 100 microns out, look at how good this performance is, right? We're getting very close to the values that we expect to see in both of these cases. And in general, that is also true if we consider the entire set. This is just one. We can expand this to everything. So this is a bit of a different view of the kind of thing that I just showed you, where now we are looking at the data distribution of the flux ratios of models in our set. So this is plotting the distribution, dealing with the distribution of our recovered fluxes to the true fluxes of every model in the set that we're pulling from. And again, at 100 microns out, it looks pretty good. On average, we are able to recover pretty much exactly the flux that we expect with error bars of about 20 to 30% of the true value. These error bars are the 16th and 84th percentile values of the data distribution that underlies this. It was going to get a little crowded if I showed you everything, but I think this is a good summary. And then the dots are the 95th and 5th percentiles of that same data distribution. So at 100 microns out, which is the wavelength regime that our group is concerned with at the moment, mostly, it's very, very good. So we can expect that if we make these predictions, they will be a good vector for going out and constraining YSO properties in the way that I've shown. Now, obviously, there's an entire left half of this plot that I haven't talked about too much yet. So obviously YSOs are also observed in the infrared, and this is a census of the wavelengths that are commonly used to observe YSOs. And the problem here is mainly one of tracked properties. See, I said that we're matching based on the source temperature and luminosity and the core mass. And these are things that correspond very well to long wavelength radiation, which mostly relates to overall dust content and like bulk source properties. But on this left side, the shape of the dust starts to matter a lot more. Like, do you have a cavity? What does your disk look like? Things like that can have a much more pronounced impact on the radiation that you get out the other end. And currently, we're not really tracking those. And the reason why we're not tracking those is because it's difficult to know which of those properties really are important for our purposes here, or how those properties should evolve as a function of time. I think we're just getting to the point where we can get consistent observations of things like disk properties, especially in like the inner regions, which do affect the SED that you get out. So I think this is evidence that more modeling work needs to be done for what parts of a YSO's evolution impact the infrared and how. And that is work that I'm very excited to do going forward, if only I could get some support. But I may be reaching out to you independently about that later. But in general, the IR is not useless as it currently stands. You'll see that on average, we're able to get reasonably close to the correct value here. It's just that you're taking these huge uncertainties on board. These are some hefty uncertainties, but that's kind of a consequence of the state of IR modeling as it currently stands. So, it's good to see it, at least. Now you know what you're dealing with. Now, this is, I think, a reasonably good evaluation of how our predictions perform, but that's not the only thing that this framework can do for us. I want to revisit a comment that I pinned earlier, which is to do with the classes and stages of YSOs. See, where we left it, I essentially said that those numbers don't really make a whole lot of sense to take too close, take literally, because there hasn't been any work associating them with actual models of protostellar evolution that make physical sense. But that is the very thing that I have done in this framework, right? It exists to take models from my set and tell us which ones are consistent with particular evolutionary theories. So if we revisit class stage confusion in the context of this framework, we can get some pretty interesting results out. So these are confusion matrices that are based on models that are selected in proximity to the evolutionary tracks that I showed you a few slides ago from that same population of YSOs, generated according to isothermal sphere and turbulent core accretion histories. Again, left, right. And the picture has changed a fair amount. Right out the gate, stage 1 class 1 models make up almost half of this matrix, and certainly a clear majority of the class 1 column in both of these cases. So the correlation between stage 1 and class 1 is very, very good. If you see something that looks stage 1 according to these models, or that looks stage 1 according to these models, it probably is. There is some confusion possible, but in general, this matches what we expect. However, if we look at some of the other classes, that expectation can kind of vary. Both of these class 2 columns are much more confused in stage than class 1 is, which points to more avenues for confusion of class 2 YSOs. Again, I think this is due to looking along sight lines that reveal the central source much more than you might expect from a generic conception of a stage 1 or stage 0 model. If you see stellar contribution, you get something that is probably a later class than you might otherwise expect. So this tells us that according to the scenarios that go into the generation of these matrices, that is a distinct possibility that that might happen. As well, I'll point out that both of these matrices are different than, well, I'll say, sorry, what I mean to say is that these matrices are both different from just the non-model associated confusion matrix, but they're also different from each other, right? If you look at these numbers, you will notice that stage 0 and 1 make up a higher component of the turbulent core matrix than they do the isothermal sphere matrix. Because turbulent core YSOs have accelerating accretion rates with time, they spend a lot more of their lives at earlier stages proportionally than isothermal sphere YSOs do, which means that if you look at the same population of YSOs in class and use these matrices to map back to a stage population, you'll pull out different results for what the population of YSOs actually looks like from an evolutionary perspective, which I think is, again, a very interesting result that you can get using this framework that goes right to the heart of a lot of things that we know or we think we know about how YSOs evolve, right? So I am excited about the future development of this framework. This is where it currently stands, and I've got more stuff coming down the pipe. So I'd like to close this talk by sort of mapping out what I'm doing right now and where I'd like to go going forward, which is making models of YSO populations using the framework that I've developed. So we have the capacity to produce individual models of YSOs that evolve according to particular accretion histories. Now we need to think about how actual populations of YSOs that we go out and observe in star-forming regions might be reasonably compared, or how we can make things that actually compare to what we expect to go out and see when we look at actual regions that are forming stars. So this is a rough roadmap for how I intend to do that. And the YSOs that I generate, the evolutionary tracks that make up their base, are parameterized by the final stellar mass that a YSO will attain at the end of the track. So if we draw a set of final stellar masses from an IMF and combine those final stellar masses with some accretion history, we will be able to produce a collection of modeled YSOs that will evolve according to some accretion history and eventually result in some IMF, which allows us to evaluate along the same, in the same way as I've shown between accretion histories for more theoretical quantities, right? This allows us to make a basis for what quantities might actually be directly observable through the observed fluxes of YSOs. But this isn't quite the end, because we also have to think about timing a little bit more than we have at the moment. Because obviously, if you look at a star formation region, there is going to be some questions about the history of that region, which are things like, does everything start in a single event? Does that single event result in things beginning to accrete around the same time, or does it result in things finishing accreting around the same time, or is it both? How efficient is mass accretion? Is the star formation history more random? Do things just sort of pop up, as they cool sufficiently? These are all considerations that can go into a star formation history, which will allow us to align our modeled YSOs accordingly, which will provide more of a basis for a thing that you might reasonably expect to go out and see. And so the future of this work looks a lot like this, where we can now generate expected distributions of flux, which is what you're seeing here. These whisker plots are 1 millimeter flux distributions for clusters that I've generated following a turbulent core accretion history in this case. And the difference between these two plots is the star formation history. On the left, everything starts in a single event at roughly the same time. And on the right, it's a single event that ends roughly around the same time. And clearly, if you look at the distribution in the middle stages here, it looks pretty different. You should be able to distinguish between these scenarios, right? If you catch a population of YSOs in this time frame. And further, this isn't the only axis that we can evaluate along. So this is the same thing, but now the right plot, instead of varying the star formation history, varies the assumed IMF that goes into the population. And again, it's distinct in the time that stars are actively accreting. So you should be able to distinguish and therefore observe the IMF, or observe some combination of all of these theoretical parameters. And I'll also highlight that not only are these distributions different, but if I flip back and forth between these, they're different in different ways. So this points us to the future, which is going out and comparing these simulated distributions to actual data, which is here. So this is a sample of 1 millimeter fluxes from observed YSOs with the ALMA IMF program. And this is going to be the start of, I think, a very comprehensive overview of what scenarios are possible when considering observed data with clusters that I've generated according to a wide range of theories about how stars form. And I think this has, I'm very optimistic about the transformative potential of this framework that I've developed. And I hope you are too. So with that, I'll close here and I'd be happy to take your questions. Thank you for listening.
So because we started late, we are going to run a bit late, but if you are able, I encourage you to stick around. We have the room, so no need to worry about that. And we have a question online from Caitlin, so we'll go ahead and start with Caitlin.
Thanks. It's a really interesting talk. I have a quick question. Maybe you said it and I missed it, but how are you dealing with the issue of the accretion shock on the YSO? I mean, this goes back to, I guess, Hosokawa and Baraf maybe 15 years ago, showing up a big difference depending on what you did with the accretion shock. So does that matter in any of the sort of follow-ons from these models?
Right. Okay. So good question about the observational ramifications of other things. Currently, we've sort of limited ourselves to pretty bare bones accretion history models that currently don't really take that sort of thing into account. I think that is a very good avenue for expansion of this. I think that can be added hopefully that can be added hopefully there's a model that can be developed to sort of add in effects from things like accretion shocks into predictions sort of post facto.
But I thought anytime I mean, I think this is in all the often, all of like the oftener models that you're comparing to as well, right? If you must have a temperature and luminosity for your YSO, and to correlate that with an accretion history, I think you have to make an assumption about the efficiency of the accretion shock on the star. There's usually like a parameter, but do you make do you make that assumption? Do you make one or the other assumption? You're not varying it. I get that.
Right. Okay. Yeah. No, I think I see what you mean though. So yeah, the accretion histories that we are using follow a model from Offner et al. 2009. And the accretion shock currently, I think, is part of the prescription for the total luminosity of a YSO that goes into the model that comes from the protostellar evolutionary tracks that we're following. So in a sense, we are kind of tracking that as a contributor to the luminosity of a YSO.
Okay, great. Yeah.
Yeah. So the L star that we're following is the total luminosity, which does include accretion shocks.
Thanks.
Yes.
Thank you very much for your talk. I have many questions, but I'm going to ask you just one related to the plot that you're showing now. So I think that you did a lot of work by including all of these different physical mechanisms into your simulations as well. But I just want to mention one that becomes very important, like for the second beam in your plot, which is planets. So we know now that planets are formed very early in the stage of the disk, probably like by half mega year.
Yeah.
You already have some in there. Planets start carrying substructors trap dust. And so when we look at starting regions at 1 mega year, or even 3, 5, 10, we have many objects that have managed to keep their material, so they are very millimeter bright. So how far into age do you think that you can connect your simulations to the observations without including the planets that are being formed in those disks?
Right. Okay. I think that's a great question. And it's a region of sort of theory space that so far I haven't really had the capacity to explore much. I think I would expect planets generally to occur more around like the low mass end of the distribution here. So like all this stuff. So I would say that they will affect this part of the distribution probably by adding some additional flux if they're millimeter bright. But I think that's sort of pending the ability to link the evolution of protoplanetary disks as planets form with the accretion histories that we're assuming, which is something that I've been thinking a little bit about how to do recently. But So I suppose in general, if the timescales are such as we suspect from current understanding, probably that does affect this distribution, probably starting here. So I think it is a good thing to be able to include as something that we expect to happen. Does that does that answer your question roughly? Okay.
We have a question in the chat. Rajat wants to know, where can we access the training data to try some modeling at our end?
Right, okay. So currently, this is stuff that is in the publication process. So I intend to release a lot of this modeling infrastructure as things are published. So currently what there is access to is just the base set of YSO models. That is out there. And laying out sort of the general method that I'm following here, if you can sort of replicate that, you can use that as training data. But I would say currently it is inaccessible to you, but I will fix that.
I imagine once the paper is published, GitHub probably.
Yeah, I'll work up a software tool and a data release that'll go along with all of this work.
Dominica.
Yeah, hi, thanks for the talk. I wonder, what about the outflows, like jets outflows and everything? They have also contained a lot of gas and the ALMA observations of that. So if you look at your object, directly to the object, so you might also see more gas, I guess.
Yeah, so I think that's absolutely a fair thing to say. I think mostly that falls in the genre of features that we've been marginalizing over to get very general continuum predictions. But I do expect that as we tighten down on particular scenarios, that outflows will play a role in the expected. So that this is very much a base framework, I think, for modeling this stuff. And that's why there's a lot of potential to grow in a lot of different directions, that being one of them. So I can't say more, but it's taken a lot of effort to get this up and running. But I think that's definitely something that can be added by restricting to particular geometries that go along with sort of the structure that's implied by an outflow. Like make sure that there are cavities included in the sample that you draw from, and then add in a prescription for how much mass should be loaded into the outflow and how that should appear at the wavelengths that are being considered.
So in your evaluation, should you also include like removal of the material from the system? Right,
yeah. Currently, no. Currently, it is very much a paradigm where everything that starts well, indirectly, I would say that we kind of touch removal a little bit by including an efficiency of mass accretion. But mostly that's just parameterized with like a single value to date, but that's something that can be played with. That's like a free parameter within the modeling.
I have a question. So, as I'm sure you know, low mass stars are known to have variable accretion rates, not just changing with time, but bursty, episodic. And there's increasing evidence that that's pretty likely for high mass stars as well. Do you expect episodic accretion to significantly change this results, or because you're doing essentially stellar population work, is it not expected to be that much of an impact in terms of what you see at the population level?
Right, okay, that's a good question. I don't know if I have a solid sense of the second half of whether I expect it to manifest strongly at the population level, but certainly individually, I do expect that to matter. So all of our accretion histories have been pretty smooth and in many cases accelerate with time. That's sort of one of the classical solutions to like the luminosity problem, such as it is, but obviously bursty accretion rates are another one that we've thought about how to implement and could be plugged in to this infrastructure pretty easily if we had bursty accretion rates to work from, right? If we had a way to generate evolutionary tracks that with bursts, that would affect things like the total luminosity, which does at any given time because of accretion shocks, which does impact which models will get picked as proximal. So yeah, generically, I would expect low mass stars in particular to be pretty affected by bursty accretion, though I don't know how much of an impact that'll have at the population level because I'm not sure how stochasticity is going to factor in.
And they tend to be, well, I know more about it at high mass levels, but they're brief, certainly at the high mass level.
Yeah, definitely the variable accretion histories are a thing that I very much want to expand this to include. And I've done a little bit of work on adding tapering in. Currently, most the accretion histories that I've drawn from so far they just sort of cut off when it's done. So there's plenty of ways to tune the theory space here or expand it to include things like that, I am going to get to.
I ask a sort of follow-up question on this. Can the models you generated, the parameter space you have sort of cover the burst in the accretion rate for the very low mass stars? Like it's in short way, like what are the accretion rates included in the models? Or are you varying as the parameter, as the accretion rate, or just fix them?
So if I can go back to where was it? It's a long talk. This guy, right? So these are examples of the accretion rates that we're using, which are some of which are fixed. Our prescription for isothermal sphere accretion is a fixed rate as a function of time, and some of which are time variable. So what you're looking at here is representative of what we're doing, which can extend to the low mass end. It does manifest differently. So you can just imagine some additional accretion histories on here that are a bit more wobbly or a bit more bursty or tapered or any.
So, and just to follow up again.
Yeah, no, go ahead.
Same plot. So just from ignorant intuition, I would think that younger objects that have more material around would have a higher accretion rate compared to more evolved objects that have less material around. So if I look at the accretion rate, I would expect the accretion rate to be higher for younger objects. But isn't that the opposite to what you're showing here?
In this case, yes. For these models of accretion, that is the case. And I think that's mostly because of the way in which the theories are designed. Turbulent core accretion, to my understanding, is meant to be sort of a little bit of a runaway train effect, where you're able to get really dense cores that start out accreting slowly, but then as they become more massive, they attract mass more readily, and you get more and more as they go on. And that's kind of the case for competitive accretion too, where everything sort of gets seeded at the same time at roughly the same mass, and then they compete. And the more massive you get, the better you are able to gain more mass with time. You steal it from like everything around you. So I think that's sort of a function of how the theories have been conceived and implemented. But certainly there are prescriptions for accretion rate that do taper as you propose. And they can also go on this plot. Yes.
So first of all, great topic, really impressive work. And others, because to go from the YSO modeling to IMF and stable population, like, do you take into account, for example, multiplicity fraction?
Great question.
Because sometimes you can have a lot of massive stars are usually compliance, right? And you can have mass exchange between them. So that should affect also the transition from YSO to the final star.
Yeah, absolutely. Yeah, multiplicity is something that we are considering. Currently, as I've framed it, it is very much a one core, one star approach. But obviously, multiplicity is something that we expect, particularly in higher mass systems. So I think currently our our idea to factor in multiplicity is to have some fraction of the stars that we generate instead be represented by sort of binary evolutionary tracks, where we consider two stars of roughly equal mass making up one draw from the IMF and seeing how those two evolve as they gain mass as a function of time. That's something that I think can be refined, particularly, you know, as we learn more about how the fraction of multiple systems, and can extend to 3 and 4 star and more systems. But that's sort of the basic concept for how we're going to factor in multiplicity. But yes, and that obviously is going to change the shape of the flux distribution because, you know, they're going to power radiation for the YSOs differently as they evolve.
The second very short question is, because you say that making the GWST, are you also doing it with Gaia?
So I have not personally convolved a lot of things with Gaia, but I have put in a script that allows you to pull from the SVO and convolve whatever you need from there for your own purposes. I think, you know, that's probably better long-term than me building up more resources and having to download like over 50 gigabytes of material every single time. But yeah, so it can extend absolutely to Gaia. And I think already has from what I've heard from groups working with Gaia data.
Last call for questions. Any last questions online? All right, well, let's thank Theo again for an excellent talk.